before we dive deeper into the abstract theory of linear algebra, let's look at another important area of application. This area of application is called numerical optimization, and we look at a particular class of problems that have been extremely successful and useful across all the engineering and science disciplines, and also in economics and business administration. What I'm talking about is, of course, linear programming. And the reasons we're looking at this is really twofold. First of all, it's a nice and powerful application of linear algebra that everyone should be aware of. And second, it serves as a good motivation for the material in the rest of this course, as you can see how useful and powerful linear algebra can be in practice. The invention of linear programming started in the 1940s and has seen a rapid development since then. In particular, with the rapid development of computational hardware, linear programming has become an important and powerful application of linear algebra for many engineering problems and also problems in logistics, economics, and the sciences. And the reason is that linear programming allows the statement of complex optimization problems by using only simple, namely linear expressions using vectors and matrices. Linear programs are thus a very important subclass of convex optimization programs. Today, a large number of commercial and open source software packages are available for the solution of linear programs. As a result, linear programs can be solved extremely fast and efficiently and up to very large problem instances. Since linear programming is such a powerful tool, it is therefore important for a modern engineer to be able to recognize a linear program when he or she encounters one in their daily work. And second of all, it's important to have the ability to model a real-life problem as a linear program. And this is what this chapter is partly about. So what are the ingredients of a linear program? The first thing that you need to know about are linear inequalities. In chapter 2, we have already discussed about systems of linear equalities in Rn. Now, linear inequalities can be used to efficiently define particular regions of the space Rn. So what exactly do we mean by a linear inequality? A linear inequality is defined by a given vector A in Rn and a scalar B in R, and then the linear inequality is either that the inner product of A with a vector x must be less than or equal to B, or this inner product of A with x must be greater than or equal to B. And that in fact defines a half space in the space Rn. To illustrate this fact, let's look at a little example. And of course, it's the easiest to draw in a plane, and therefore we consider a vector A in R2 that in this example is just defined by the entries 1 and 3. And this vector A is drawn in a plane down here. So it points to the point 1, 3. From basic linear algebra, we know that the inner product of the vector A with the vector x, so A transpose x, is given by the following formula. It's equal to the length of the vector A, so the 2 norm of the vector A, times the length of the vector x, times the cosine of the angle between the vectors x and a. From this formula, we can observe the following. The inner product of a vector x with a is non-negative if the angle alpha is somewhere between minus 90 degrees and plus 90 degrees, because that's the range where the cosine is positive. So if we draw a perpendicular line onto the vector A, then the set of all vectors x that have a non-negative inner product with A is exactly the set of all vectors that lie above this line in the same direction of A, or which fall exactly onto this perpendicular line. Conversely, the inner product of A and x is less than or equal to 0 if the angle between these two vectors is somewhere between minus 90 and minus 180 degrees, or between plus 90 and plus 180 degrees. And if we again use our perpendicular line here, then this is exactly the area below this line or on this line. So we conclude that in our example, the perpendicular line on A divides up the entire plane into two half planes, where the upper one is the half plane that's defined by the inner product of A and x being greater than or equal to 0, and the lower half plane is defined by the inner product of A and x being less than or equal to 0. And this idea generalizes to higher dimensional spaces, where this perpendicular line turns into a hyperplane that divides the higher dimensional space into two half spaces. And again, these two expressions exactly divide the space into two half spaces. Now, if we don't have a 0 here, but for instance a positive real value, this just means that this hyperplane gets shifted into the direction of A accordingly. And if we have a negative number here, this means that the hyperplane gets shifted into the negative direction of A. But it still remains a hyperplane whose orientation is defined by A because it's perpendicular to A. It just gets moved in a parallel way by the scalar on the right-hand side. An example of this can be seen at the bottom of this slide, where we have the same vector A as before, but now we don't have a 0 on the right-hand side, but we have a 3. And we see that this causes the dividing hyperplane here to move in the direction of the vector A. And now we're interested in the half space that's defined by A transpose X is less than or equal to B. So in the half space that's below this dividing hyperplane. Note that the common way to draw this in the literature is not to mark the target hyperplane, but rather the common way to represent this is to cross out the hyperplane that's excluded by our linear inequality. Moreover, it's custom to use a less than or equal to inequality to define a half space. And that's without loss of generality, because if we have a half space that's defined by a greater than or equal to inequality, we can always multiply this inequality by -1, and we get another vector A, which is now minus A, and another scalar B, which is now minus B, such that this half space defined by this inequality is the same as the half space defined by this inequality. Another way to see that a linear inequality of the type A transpose X less than or equal to B really defines a half space in Rn is to decompose any vector X into two components, one that's parallel to A and one that's perpendicular to A. So we can write X as the sum of X parallel and X perpendicular, where X parallel points either in the same direction as A or in the opposite direction of A, and X perpendicular is perpendicular to A. By the properties of the inner product of A transpose with X parallel is now equal to either plus or minus the product of the two length of the vectors, because the angle between A and X is either 0 degrees, in which case the cosine is +1, or it's 180 degrees, where the cosine is -1. And the inner product of A with x perpendicular is 0, because the angle between x perpendicular and A is either plus or minus 90 degrees, and so the cosine is 0. By linearity of the inner product, we therefore have that A transpose times the sum of these two components is equal to the two inner products, so A transpose x parallel plus A transpose x perpendicular, where the second term is 0, and hence we're only left with this first term, where the plus or minus again depends on whether A and x parallel point in the same direction or in the opposite directions. What we can conclude from this is that only the part of x that points in the direction or in the opposite direction of A counts towards the inner product, and we can simply neglect any direction of x that's perpendicular to A because it does not affect the inner product. A system of linear inequalities, which is also called vector inequalities, is defined analogously to a system of linear equalities. So now we don't just have a single inequality, but we have multiple inequalities where the vectors A are stacked up in a matrix and the right-hand sides are stacked up in a vector. The way this should be interpreted is that all of these linear inequalities need to hold at the same time. So the vector inequalities given by ax less than or equal to b represent the intersection of a finite number of half spaces, and in particular as many as there are rows of the matrix A. And such a set where we intersect finitely many half spaces is also called a polyhedron. Now let's look at this from a graphical perspective. Definition 3.1 states that a polyhedron is the intersection of finitely many half spaces, as shown here on the left-hand side, where we're just intersecting two half spaces. And a polytope is a bounded polyhedron, meaning that we're intersecting so many half spaces that what we get as a result is a bounded set. Note that a polytope is a special case of a polyhedron because a polyhedron may be bounded or it may be unbounded. With this knowledge, we can now proceed to the definition of a linear program, which has the following general form. We want to find a vector x in Rn that minimizes the inner product of x with a given vector c, such that x falls into such a polyhedron or a polytope that is defined by a given matrix A and a given vector B. In this linear program, which is also known as an LP, x is called the decision vector. It's the unknown of the LP and needs to be computed. The first expression is called the objective function, since it's an inner product of x with another vector c. It is a linear function. Similar to flipping the direction of the inequalities, also the maximization can be included without loss of generality, as it can be flipped by just multiplying the objective function with a -1. So maximizing the expression c transpose x is the same as minimizing the expression minus c transpose x. The part to be is what we've already seen before, namely a set of vector inequalities, and in the context of an LP, they're called the inequality constraints. As we have seen, they describe a polyhedron, or in case if it's bounded, as a special case, this could also be a polytope. Note that equality constraints, such as A transpose x equal to B, can be realized by the general form on top of the slide, by simply including two inequalities with opposite directions, so A transpose X less than or equal to B and A transpose X greater than or equal to B at the same time. Another general form of LPs includes these equality constraints explicitly by adding another set of vector equalities to the LP. Analogously to a linear equation system, let's also look at the solution cases for LPs. And that's summarized in fact 3.2. So consider any linear program in a standard form such as the standard form 2 or 3, and let P be the set described by its constraints, which is also called the feasible set. We only have the following solution cases that can occur. First, there may exist a unique solution that we call X star, which is one of the vertices of the feasible set, so the polyhedron P. Second, there may exist multiple solutions with the same objective function value. One of the solutions is then, or at least one of the solutions, is then a vertex of P. Third, there may exist no solution, and that's exactly the case if P is empty, so intersecting so many half spaces that there's no feasible point left. And fourth, the problem may be unbounded, namely if the feasible set is a polyhedron that is unbounded and the objective function is such that the value can be minimized arbitrarily without a bound inside the polytope P. Now, how do we solve LPs? As we have seen in fact 3.2, if a solution to the LP exists, there's always at least one point X star, which is one of the vertices of the feasible set, meaning the polyhedron P. So in theory, we could just go through all of the vertices of P and check which one is the best. However, this would be far too expensive, as a simple example shows. If X is a 100-dimensional vector and the feasible set P is just a hypercube in R100, then P has 2 to the 100 vertices, which is approximately 10 to the 30 vertices. Suppose our evaluation of one vertex were really fast, so it takes only 1 picosecond, which is 10 to the minus 12 seconds. Even then, the process of checking all of the vertices takes about 4 times 10 to the 10 years. So that's about 40 billion years, which is much longer than the age of the Earth. And in reality, a decision vector of dimension 100 would be considered as rather small. In fact, state-of-the-art algorithms are now able to solve problems of many thousands of decision variables or even millions of decision variables in a reasonable period of time. Over the past few decades, very efficient methods have been developed for solving LPs, and these methods heavily depend on linear algebra. Due to these methods, problems with hundreds of decision variables can now be solved in the range of milliseconds, and very large problems with millions of variables can be solved on normal desktop computers. And here's a quote from Stephen Boyd, who is one of the world's leading experts on optimization methods. And the quote says, "If you can store the problem, you can solve it." And that's how efficient methods on linear programming have become nowadays. So thanks to all of these new methods, many commercial and open source software packages are now available for solving LPs. As I've already mentioned, they're all built on basic linear algebra, and certainly every one of you has one already installed on her or his computer. For instance, a commonly used one is the function linproc in MATLAB. For an example, let's look at a small case study of a transportation problem. In this transportation problem, we suppose that we have a total of 3 plants which produce products that are then shipped to retailers where these products are sold to customers. The shipment of a product from a plant to a retailer incurs transportation costs, and since the plants and the retailers are set up in different locations, the shipment costs differ depending on the plant that we're shipping from and the retailer that we're shipping to. The specific shipping cost from plant I to retailer J is called Cij, and the values of all of these shipping costs for all I from 1 to 3 and all j from 1 to 3 are given. Moreover, the maximum production capacity of each of the plants, which equals to the maximum supply Si for plant I, is known and cannot be exceeded. And similarly, the demand dj for each retailer j is given and must be met exactly. After realizing that this type of problem can be modeled as an LP, our motivation in this example is to actually formulate this problem as an LP. So what we have to do is some corresponding mathematical modeling work, and the first step is to define the decision variable xij as the quantity that's shipped from plant I to retailer j. So it's the decision variables, and the CJs are, as defined on the previous slide, the shipping cost per unit of the product. So the total shipping costs that we incur is given by the sum over all plants I from 1 to 3 over the sum over all retailers from j equal 1 to 3 of the specific shipping costs times the shipping quantities. And this total shipping cost is minimized with respect to our decision variables xij. Now, by defining the cost vector C as the collection over all 9 specific shipping costs and the decision vector x as the collection over all 9 shipping quantities, we can express the total shipping cost by this type of linear objective function. Clearly, if we just minimized this quantity, we would get minus infinity because the optimizer would just choose all of the shipping quantities to be very negative, and hence the cost would become very negative, and this would be the optimal solution. But that's of course not what we want. So in order to get what we want, we also need to introduce constraints to our linear program. And the first constraint is that for each of the plants I, the total amount to be shipped must be less than the available supply Si. So if I sum the shipment quantities to all of the retailers from j equal 1 to 3 that gets shipped from plant I, this must be less than or equal to the available supply Si. So we have this constraint for all of the plants I equal 1, 2, and 3. Again, we can model this by using vector notation and defining our linear inequality vectors and right-hand sides appropriately. Note that for the first plant, we need to sum up the first 3 decision variables, and hence the inequality vector A looks like this. For the second plant, we need to sum up the second 3 decision variables, and hence our linear inequality vector looks like this. And finally, for the third plant, we need to sum up the last 3 decision variables, and hence our linear inequality vector looks like this one. And since these three inequalities must hold simultaneously, we stack them up into vector inequalities, where the matrix A consists of the three vectors A1, A2, and A3 stacked up as rows of the matrix A, and the right-hand side B consists of the three available supply quantities S1, S2, and S3. The modeling of the constraints due to demand satisfaction works in a similar way. Recall that for each retailer J, the total amount of products to be received must be equal to its demand dj. So the condition that must be satisfied for each retailer J from 1 to 3 is that the sum over all shipping quantities from the plants I equal 1 to 3 into J must be exactly equal to dj. Now we again bring this into a vector notation by defining the three vectors C1, C2, and C3 in this way. And then, since all of these three demand satisfactions must hold at the same time, we have to stack them up as vector inequalities. And we do that as before, namely by putting the three linear inequalities on top of each other. And that's how we obtain the matrix C. And then the right-hand side of these equality constraints are given by the demand quantities D1, D2, and D3. And we call the right-hand side by a lowercase d. In addition, what we must have, of course, is that all shipping quantities, which are our decision variables, must be positive. So xij greater than or equal to 0 for all I and all j. Note that this condition can be expressed by using the 9 by 9 identity matrix, and it reads as follows: identity times our 9-dimensional decision vector has to be greater than or equal to 0. So each of the elements of the decision vector has to be greater than or equal to 0. And we can simply reformulate this as a vector inequality with a less than or equal to sign by multiplying it with a -1. So we get minus identity times x less than or equal to 0. So altogether, the LP formulation of the transportation problem reads as follows. We want to minimize the total transportation cost that we have modeled by C transpose X, subject to the supply constraints, which we have modeled as AX less than or equal to B, and subject to the demand constraints, which we have modeled as CX equal to D, and also subject to the shipment quantities being positive, which has been modeled as minus IX less than or equal to 0. Now, for the sake of an example, let's assume some specific numerical values for the shipping costs. And this table here shows the values of all of the shipping costs Cij for all of the plants I from 1 to 3 and all of the retailers J from 1 to 3. Moreover, we pick particular values for the supply limits, which are 20, 30, and 30 for the three plants, and also the demands that need to be satisfied, which are assumed to be 25 for all of the three retailers. Now, we can just use any standard LP solver. In this case, it was MATLAB's linproc command in order to solve for the optimal shipment quantities. The optimal shipment quantities are shown in the table below. We call them Xij marked with a star. So the star stands for the optimal value. And the indicated values represent the optimal shipment quantities between each of the plants 1, 2, and 3 and each of the retailers 1, 2, and 3. By the way, we have made the corresponding MATLAB script available on Moodle, so you can just download it and play around with it, meaning you can change all of the given data and calculate your own optimal quantities to be shipped between the plants and the retailers. Of course, this was just a small toy problem to show you how a particular problem, in this case of logistics, can be formulated as an LP. Of course, there are many other problems out there that can also be formulated and solved as an LP. Moreover, the presented transportation problem can be made more realistic in many ways by making it much larger or more complex. So for instance, we could consider a much larger number of plants or a much larger number of retailers. We could also introduce additional layers, for example, warehouses that the products first have to be shipped to before they actually get shipped to the retailers. We could also consider multiple products. We could consider the problem for multiple time periods with or without inventory costs. We could confine the shipping routes to only contain certain routes and not allow other routes. We could have transportation capacity constraints and so on. So there's actually also a lot of research going on how to model particular practical problems as LPs in domains such as logistics or production, but also, of course, in other areas of engineering and science.